So first things first, some corrections. Actually, one big correction, which I have to make for moral ethical reasons, is I misstated a pretty important result in my haste at the end of last time. So if you remember last time, maybe let me just remind you where we left off, right? So we're looking at functions that were continuous or differentiable, right? So we defined what continuity and differentiability meant. So we look at continuity and differentiability of functions of several variables. So in mostly 2 or 3 variables, right? You were tested mostly on the ones in 2 variables because that's complicated enough. And one word about differentiability, right, was we have a subtle difference in types of differentiability we could do when you have more than one variable. One thing is if you take, right, so f of xy is differentiable at a point, let's say AB, or let's do x naught, y naught, exists a function, right, L, let's call it L of xy, that approximates f of xy well near x naught, y naught, right? So this was basically, if you have a graph, in this case, if it's a 2 variable function, we could graph it. And in certain situations, if we had this sort of way of calculating what it means for you to have a nice first order approximation to your function, and we call this, if it exists, it's called a linearization, which we did. And if your function is differentiable, then, well, we say your function is differentiable at a point if there exists such a nice linearization near that point. All right. Now, to build this linearization, we had to calculate the partial derivatives. And it turns out that the result that we want is if f has continuous partials, so let's say, in this case, so partial x of f, partial y of f, then f is differentiable. So that's one direction that we stated last time. The opposite direction is actually a bit subtle. We also have the fact that if f is continuously differentiable, then f also has continuous partials. So checking back to my notes last time, I misstated this because this is a one direction arrow. You could verify, right? We know how to verify if partials exist. We know even when you can't use the usual differentiation rules that you saw in the last test, you could still evaluate partials or try to evaluate them and see if they exist using the difference quotient. And it turns out that if your partials are continuous, then you can conclude that your function is differentiable. All right. So, however, it turns out that you need continuous differentiability to have continuous partials. All right. So it turns out that what you have, you can actually simplify this statement to the following. You could characterize you could characterize having continuous partials as f being continuously differentiable. All right. So the total statement of this should be, if f has continuous partials, is the same thing as f being continuously differentiable. So this, we sort of know what it means. You get to evaluate a partial at each point, and f having continuous partials just means that these partials themselves are continuous functions. Now, f being continuously differentiable means that at each point you could find some function, a linearization, in 2 variables that approximates f very well at each point, and the continuity of this 2 variable function means f is continuously differentiable. And it turns out that verifying any of these is equivalent to each other. All right, so that's just a subtle point that I'd like to point out that we left off with last time. All right, so let's move on to sort of the crux of the, I guess, today's class and likely tomorrow's class as well. And what we're going to do now is look at what we could do with derivatives. So far, we use derivatives, we use partials and derivatives to approximate f of xy in an appropriate sense. And today we're going to sort of package our derivatives into a pretty useful a useful quantity that we're going to call the gradient. All right. So given f of xy or f of xyz, the gradient of f at a point x naught, y naught, or let's say x naught, y naught, z naught, is the vector defined by, well, we notate it with an upside down triangle. That's called nabla. All right, so it's nabla f at x naught, y naught is equal to partial x of f, partial y of f, and partial z, or sorry, well, That'll come later. So for two variables, you take the derivatives in each, and then you evaluate these at x naught, y naught, or you can have something similar for the three variable version, and you're going to get a three-dimensional vector. All right, so here's our definition of the gradient. It's either this or this. Okay, so nothing hugely difficult here. It's just, for some reason, we have these quantities, these partials, that we know how to calculate, and we've decided to package it together into a vector. So what does this buy us? Let's take a look. The uses of the gradient. The first one, which we'll present, is finding directional derivatives. All right, so these are how, this is how f changes near x naught, y naught in directions not necessarily parallel to x or y axes. All right, so remember that these partials themselves, I just look at partial x, that's like if I have, right, if the screen here is a sheet of metal, f is some function telling you let's say the brightness at a point xy, then partial x is measuring how the brightness changes as I near a point when I move parallel to the x-axis, and partial y is how the brightness changes near a point if I go up and down, right? If I move parallel to the y-axis. But there's not particular any reason, no particular reason why we can't move in arbitrary directions, right? You might ask, how does the screen brightness change if I'm moving, diagonally, for example, or maybe along a different slope. So there's infinitely many directions, in a sense, a circle of directions in a sense that you could go to in two dimensions, and you might care about how f changes generally. And it turns out that the gradient's useful for this. So we'll see very soon why this is true. The second use of this is geometric, and this is finding tangent planes to surfaces not necessarily given by graphs. All right, so remember that where we left off was we found what a linear approximation was, the graph of a linear approximation. So if I have a function of two variables, right, this is its graph, and I can find the linear approximation of f near some point. And when I basically give you the graph of that plane, that gives you the tangent plane to a point on this graph. Now, the issue is, well, not really an issue, but this is not very general because there are surfaces that are not necessarily given by graphs, right? We saw this when we looked at implicit differentiation. You can't always write everything nicely as a graph. So you might also want to care to find tangent planes to surfaces when it's presented in forms that are not immediately a graph. So it turns out the gradient is also useful for this. And the third big reason to this is to finding minima, maxima, and optimization. All right, so the huge uses of gradient that we'll focus on for this class and next are these three. Okay, so yes, gradient descent is certainly an algorithm used in machine learning models and general optimization. I'll have more to say on that when we reach number 3. Okay, so as you'll see, this gradient method here is pretty important. Or this quantity, the gradient, is important to know. So let's start with the first one, which is directional derivatives, and what I mean by directional derivatives. So let me recall something, which was what I said earlier in words. So the partial, suppose your functions here, I'm going to not write this down, but suppose everything's very nice, all right? So you don't have to worry about any badly behaved things. Partial x of f at a point x naught, y naught, let's say we're looking at two variable functions here. But directional derivatives also work in three variables. So let me just note that here. 3 variables or more. So let's say I have a partial here. This is defined to be the limit as h goes to 0 of, let's say, x naught plus h, y naught minus f of x naught, y naught all over h as you take this limit. So geometrically, what is this? Let me do a nice graph for this first. So let's say I have a graph, right? So this is my graph, z is equal to f of xy. And let's say this is my point, let's say x naught, y naught. Then what am I doing here? X naught plus y at y naught as h varies, that's really just giving me a line here, right? That's giving me the line that's going in this direction here. There's a line here. This line is this is a line x naught, y naught plus h10, right? This expression here is exactly what this is. And what is this doing? That's allowing me to slice vertically here to see what the slope of this curve is, right? So this curve here is formed by, well, I take a line here, I sort of slice vertically by this plane. It traces out, or it intersects along my graph in this curvy line, and I could evaluate what the slope of this curvy line is at instantaneously at this point. But there's no particular reason why I need to choose this particular line, right? I might be curious and say, okay, well, what if instead of the direction 1, 0, I choose a direction vector AB. I could also draw another line lying on the xy plane going through the point x naught, y naught. And so this line here would be x naught, y naught plus, let's say, h AB. And so if I'm going along this line here, I could ask a similar question, which is, right, could I slice this? I could slice my graph this way and look at the curve this traces out. And then I could also ask what the slope, what the tangent line is to this intersection line, right? And that's going to get me another quantity. In fact, that's going to get me how my function is changing along this direction given by AB through this point, x naught, y naught, right? So we could generalize the partial and ask, right, if given a point x naught, y naught, and a, let's say, unit direction, u is AB, what is the change of f at the point P in the direction u? All right, so we call this point P. So this is the directional derivative of f at P in the direction u. And the notation is you have capital D, your vector u at the bottom, and f at x naught, y naught. And this is given to you by the limit as h goes to 0 of f at x naught plus h a. Maybe I'll make sure in this case if it's u here, then, well, I'll keep u here. Remember, u has components a and b, and u is a unit vector. Then you have f at x naught plus ha, y naught plus hb. This is f evaluated everywhere along this line, right? X naught plus ha, y naught plus hb gets you somewhere on this orange line, and you evaluate f here, and that's going to get you somewhere on this red intersection. And you want to take the difference quotient with respect to this. We'll subtract off the base point, and you divide out by h, and you take this limit. All right, so this is the definition of directional derivative. And once again, this looks in general pretty complicated. So how do we calculate this? Well, we use a gradient. It turns out that whenever f has partials that exist and is differentiable at x naught, y naught, then its directional derivative in any direction, instead of having to evaluate this from scratch, you could just take the gradient of f at the point x naught, y naught, dotted with the direction u. All right, so in this case, this would be partial x of f, partial y of f, dotted with ab. In 3 dimensions, let's say if u is a unit vector with abc components, then we have the same, and that gets you the directional derivative, and the direction u at a point x naught, y naught, z naught is the gradient at that point dotted with u, which I guess you could expand out similarly as above with a z derivative as well. For now, let's do a few examples on directional derivatives. All right, so maybe I'll do this. This. Okay. So examples. So let f of x, y, z be the function xy minus xy squared minus z squared. What is the directional derivative of f at 2 minus 1 minus 1 in the direction 5, 1, 7? So I'll make a remark here before you calculate it away. Hint, make sure the direction has unit length. All right, So let's do some calculations first. Does someone want to volunteer just the gradient calculation? What is the gradient of f? So even before plugging in the numbers, what's the gradient of f going to be in this case? So what's partial x of f? All right, so partial x. In the x component, you're going to get a y minus y squared. And then in the y component, what should that be? Right, that's x minus 2xy. And then you have a 2 minus 2z. Okay, now, so what's this at the point 2 minus 1 minus 1? Well, the gradient at this point, we'll plug this in. So you have minus 1 in y. So this is, you plug in minus 1 here, right? That's minus 2. Here you have 2 minus 4. That's 2 minus 4, so that's 6, I hope. And then minus 2z. Z is minus 1, so this is plus 2. So at least one person has gotten the same answer as me. We're either both right or, both wrong. But look at the direction vector now. So you need to make this unit. All right. So what's the reason for making this unit length? It's sort of like standardizing your ruler, if you would like. It's just like how here, right, when we're taking the usual partial derivative in x, right, we always just want, you want to increment by units of x, right? So there's nothing in front of the factor of h here. Right, remember that when we didn't do these fancy directions, we were just stuck with partial x, we're really just moving one, we're incrementing in the direction 1, 0, not like 500, 0 or minus 4, 0, right? It's always just 1, 0. Similarly, you want to sort of, in any direction you go, you want to make sure that you're incrementing unit length. All right, that's just, there's probably more rigorous ways of writing it out, but intuitively, I hope that sort of makes sense. You don't want to sort of rescale the speed at which you're going in a certain direction. You want to make sure that everything's just incrementing unit length. So it's important that when you apply this formula, that the direction vector here is always a unit vector. So in this case, it's presented to you not as a unit vector, so you have to do the hard work yourself. All right, so 517, the magnitude of this is the square root of 5 squared plus 1 squared plus 7 squared. So what is this, like 49 plus, right, so this is 25, oh shoot, so this is 25 plus 1 plus 49 is root 75. So this means that for u, let's take u to be 1 over root 75, 517. Let's now plug in. So our 2 minus 1 minus 1. In this direction, our directional derivative is just this. Now we could plug in our values. We had minus 2, 6, 2 dotted with 517 root 75. Oh boy, okay, so this is minus 10 plus 6 plus 14, right? Root 75. That's 10 over root 75. So let's do another example, this time in two variables. So now let's say f of xy be equal to e to the x y squared plus sine 2y, so plus x. Okay, let's say at the point at the origin, if theta is the angle made with the positive x-axis, just like in standard polar coordinates, what is the directional derivative of f at 0, 0 in the direction given by theta? All right, maybe I'll let you guys have a couple minutes to think through this, and then maybe propose your ideas in chat, and we'll go over this together. All right, so does someone want to volunteer what the gradient is at the point 0, 0? So let's take partial x of this. Partial x of this, you're going to get a factor of involving x. Involving y out front here, but you're at 0, 0, so this part disappears. X doesn't see this term at all, and you get a 1. So this is 1. And for partial y, similarly, y is at 0, you're at 0, 0, so the term here disappears, because when you differentiate this, you get some factors of x and y up front. Sine 2y becomes 2 cosine 2y, so that's a 2. Now, we have the gradient now, and we are missing a direction. Now, what might be a nice way in 2 dimensions to find a direction given an angle? Right, so you could think about polar coordinates. What's the way? So let's say I'm at a given angle theta. How can I describe a vector that is pointing in that direction that has length 1? right? So usually my vector has x component and y component, and right, so my x I could describe as r cos theta, y is r sine theta, but because I'm radius 1, I want length 1, the r is or 1, so this is just cosine theta, sine theta. Know that this only works in well, it's more easily stated in 2 dimensions, because in, we have polar coordinates, and you could sort of write this out. The same reason why polar coordinates works in 2 dimensions. It's the same reason you could write this out in this form. All right. So what is the directional derivative? The directional derivative associated with this angle theta at 0, 0 is just going to be equal to 1, 2 dotted with cosine theta, sine theta. All right. It's cosine theta plus 2 sine theta. So I'll specify here, this is x and y. And let's say I specify here's my origin, and I specify a direction here that has angle theta. Then the vector with this same direction must have a unit length. So the point here, it's your vector has unit length. So r, this radius here is 1, so it's cosine theta, sine theta. Or if you want back to basics, you draw the right angle triangle here, right? This is hypotenuse has length 1, so the length of this is your hypotenuse times cosine theta. The length of this is your hypotenuse times the sine of theta, and your hypotenuse has length 1, so that's how you get this formula. In this case, we're not in R3. This is in R2, right? This is a function of 2 variables here. You cannot do this in R3. In a sense, you'll have to specify which plane you would be taking in R3 if I were to set up this one. But this theta being the angle made with a positive x-axis, right? If this were R3, let's say this is x, y, and z is pointing out at you, then there's like a whole cone, right? There's a cone of angles that make this green, right? There's a cone on which this cone all make the same positive angle theta with x, and then you're going to have to do a bit more work to figure out what exactly u has to be. All right, you're missing a parameter here, so you can't do this in R3. You could do this in R2. The object created is not in R3. There is no object that's created here. For example, this is a two-dimensional vector. This is a function of 2 variables. This is a direction you're traveling in 2 variables. Nothing is in R3 here. Perhaps you're confusing this with the picture I drew here. This is an artificial construction. What we just looked at were on xy plane was on the xy plane. This is a graph of my function in R3. But this graph is completely artificial. I made this graph, right? In this definition here, there's absolutely no reference to this being part of a graph or not part of a graph. It's just f of xy. Z equals f of xy is my artificial construction in R3 to picture what f of xy is. But f of xy exists independent of being in R3. It's naturally defined in R2, right? And I just drew an extra dimension here to picture what this is going. But there is absolutely nothing in R3 going on in this picture here or in this example here. Okay, so well, let me go back to my outline because I forgot what I was supposed to go to next. Right, so here's a natural question then. So we figured out, it's sort of plug and chug to do these calculations. Not very interesting, but here's a question that actually someone posed in chat earlier. Well, posed the answer to in chat, but a question to consider: given f and a fixed point. In this case, let's just take R3, just to spice it up a bit. All right, let's change it up. So given f and a fixed point x naught, y naught, z naught, what direction u maximizes or minimizes your directional derivative at that point? All right, so the question here, and maybe you care about what is the value of this maximum or minimum rate of change. All right, so here's the situation. I have a point here, P, right? This is x naught, y naught, z naught. And I have a whole sphere, right? Let's say this is an R3, right? Works in R2 as well, but I have a whole sphere of potential candidates for what u has to be, what direction u I could go in. I could see how, my function of 3 variables changes in this direction, in this direction, in this direction, and a whole sphere of directions. if this were a two-dimensional function, I would have a whole circle of directions. In this case, it's 3 dimensions. I have a sphere of directions. And the question is, in what direction is my rate of change the biggest? In what direction is the rate of change the smallest? What could I say? Or how could I even begin to answer this question, right? So here's one way you could approach this problem. So here's a brief, I guess, observation. The directional derivative at this point, right, by our calculation above, is the same thing as if you take the gradient of f dotted with the vector u. So here's my vector u. And now this is a vector. This is also a vector, right? I've fixed x naught, y naught, z naught. So this is sincerely just a vector. It has some components we don't know because it's an arbitrary function, but you fix the point. It has a bunch of numbers. You could fix, and it has a bunch of numbers. It tells you its components. So if I have a dot product of two vectors, there's another way I could express this. This could be the same thing as, let's say this is my vector, grad f. If I could put these vectors, so these are vectors in 3 dimensions in this case. So if I have two vectors in 3 dimensions, I could sort of swivel my head around to look at it head first, right? So that the two vectors together are contained in the same plane. All right, so let's suppose that these vectors now are contained in the same plane, and I could draw an angle between them. Then in this setup, we know from last half of this class that this is the same thing as the gradient, the magnitude of the gradient times the magnitude of u times cosine of the angle between them. Maybe I'll write cosine. I'll write the angle in green. So this follows from the dot product rules. And now because we're looking at directional derivatives, you're assuming to be a unit vector. So this is just 1. So this is the same thing as the magnitude of your gradient times the cosine of the angle between your gradient vector and the direction you're considering. What's the largest value cosine theta could take? And at what angle theta does 1 occur, right? Just by observing this, so if cosine theta, the biggest it could be is 1, and it occurs at theta is equal to 0, that is the angle between u and grad f is 0, what should be the answer to this question? And what direction does u have to point in for this quantity to be the biggest, right? So u should be in the same direction as grad f, and when u is in the same direction as grad f, the rate of change, your directional derivative in that particular direction, is exactly the magnitude of grad f. So the answer, so let me just say this is max when theta is equal to 0, right? So the answer here is when u is in the same direction as grad f, i.e., okay, so here's a quick question. So let's say u is in the same direction as grad f. So what does u have to be? It's a unit vector pointing in the same direction as grad f. Then u is equal to grad f divided the magnitude of grad f, right? Then the directional derivative is the biggest or largest maybe. And its value is exactly the magnitude of the gradient. And so how do you decrease this? Well, you also get for bonus, right? So you have bonus, for the questions that no one else has asked, that no one asks up here, but you know that from this observation, when u is in the opposite direction as grad f, so i.e. u is equal to minus the gradient divided by its magnitude, the derivative, the rate of change of f in that direction is the smallest, and this is equal to minus, and its rate of change is equal to minus the gradient of f. Now, in what directions does f not change at all? So we figure that if u points here, you're changing the most. When u points here, you're changing the least. In which direction do you not change at all instantaneously at that point? So the question here is, I fix a point, x naught, y naught, z naught. I have a function at this point, and I'm asking, in which direction does the directional derivative of this function achieve its maximum, and does it achieve its minimum? And in which direction does it achieve 0? Does it not? Does a function in essence not change instantaneously in the direction at all? So far, we've decided that based on this calculation, for concreteness sake, okay, suppose f, you're a fly, all right, flying around a room. And at the point x naught, y naught, z naught, f here in general at any point is giving you the temperature of the room. We've figured out that if you're a fly and you're flying in the direction, let's say this is a gradient of f, so this is a gradient of temperature. If you fly in this direction, in the same direction as a gradient, you're going to increase temperature the fastest. All right, you're going to, if it's really hot, then bad luck. If you fly in this direction, the temperature is changing really fast and it's increasing the most, fastest in this direction. If you're flying in this direction at this point, it turns out that your temperature is decreasing the most. If you want to get cooler as a fly, then you better fly in this direction, because in this direction, your derivative is changing. It is the smallest value. In fact, it's the most negative. It's decreasing the most, right? So your temperature is decreasing the most if you're going this direction. Now, which direction or which directions do you have to fly in to have your temperature not change at all is the question now. In other words, in which direction u do you have to be for this to be 0? Right, so you have to be 90 degrees. So when u is perpendicular to grad f, your rate of change is 0 at that point. All right, so this could all be read off of this relationship here. Let me just end this part with a bit of application. So as I mentioned before, this comes up in machine learning, AI, all this hot stuff of late. And maybe I could give a brief overview of where this does come in. So I won't write this down because I'm not testing on it. It's not really a way for me to test on this. But in general, if you're really any statistical model, but how AI works, or a lot of these machine learning models works, is f here is a function of like millions of variables, all right? Not just x, y, or x, y, z. It's like millions of these, all right? And these are your parameters of your model, all right? So you have a function that involves absolutely huge amounts of parameters because you have a very complex model, or presumably. And what happens when you're training this model is, vaguely speaking, you have a bunch of, let's say your model is trying to identify. Well, one thing it does is you have a bunch of data that is pre-labeled. You know this data. You know that picture A here has to be has this many. Let's say picture A has a bunch of these millions of variables, and these millions of variables correspond to like the brightness of a pixel on like some sort of standardized square. All right, and you've labeled this already. You've had a human go through these, say, okay, well, this picture here, you know the data in terms of pixel, let's say pixel brightness and all that, and you know that this corresponds to the picture of a dog. All right, and this other one corresponds to a picture of a cat, and so forth. And you have a lot of these factual pieces of information, data that you want to feed into your model. All right, and so your model, first of all, to train the model, and then you feed a picture into this, so it takes in the data it sees. Your computer, your model sees is a bunch of numbers, right? That correspond to, let's say, pixel brightness at a particular pixel, and then it tries its best to label. Maybe a binary label is not good here, but it's just it tries to identify what creature this thing is. All right, and it does so for so many pictures, and the way it associates the pixels and the data with the pixel brightness and what it labels is a bunch of parameters. All right, the parameters that go into this function f, this loss function. All right, and this function f, it then compares how far off your computer's guess is in terms of reality. All right, in reality, this picture A is definitely one of a dog with these characteristics, and you've encoded this in terms of some other parameters, and your computer or your model has tried its best to guess at this, and there's some sort of metric at which your computer does a bad job, right? It needs to you have some sort of metric measuring how far off your model is to reality, how many errors there are, how bad the guesses were, and that's all encoded in a function f that's roughly speaking the loss, right? You want to minimize the loss, which means that your loss function is telling you how far off you are from reality. And if your model's really good, you want to make sure that your model almost exactly matches reality, right? So what you need to do then is to fine tune your model, right? You have a bunch of parameters in your model. You got to make sure that the parameters change in such a way such that your loss is minimized. So your loss function is f, your parameters are x, y, z, so forth, millions of these. And what you want to do is after each iteration, you have a value of your function f. for a given set of parameters, for a given set of parameters, you have the value of function f, and you realize that gives you some sort of loss, but you want to keep minimizing the loss, right? You want to minimize this function. You want to minimize this function f. So you want to figure out which direction do I increment my parameters. So I got to change my parameters somehow to make my model better. So you need to figure out which direction to change your parameters in to decrease this loss. And the way you do this is, the general scheme is gradient descent, which means you want to minimize your loss, which means you want to decrease your loss the fastest. You want to decrease f the fastest. And at any given set of parameters, your loss. Now you want to figure out, how do I change my parameters? In what direction do I change the parameters to decrease the fastest? Well, you go with the direction opposite the gradient. All right, so that's gradient descent. And now, if you're in this line of work, the tricky business here is because nothing's smooth, right? We've been doing this. Calculus is very idealized. It gives you these conceptual ideas of how to approach things because we assume things are differentiable and everything. But in reality, this is clearly not the case. You have discrete, you have massive amounts of data, but they're all discrete points. You don't know how good this loss function is. You can't really differentiate it. So there are various schemes, right? Entire research fields dedicated to how to best implement gradient descent in a discrete setting, right, or in a non-smooth setting. So there are various ways for people to do this, and these are very active areas of research. All right, guys. So let's just do an exercise here for you to do at home, which is, let's find the maximum. What direction does f for x to the fourth y minus x squared y3? Actually, let's say this is a function, two variables. Does this achieve its maximum rate of change at the point xy is equal to 2 minus 3? Let's say unit direction, just to make sure. Okay, so maybe in the interest of time, I'll leave this as an exercise, but this is basically just find the gradient. Okay, right. So let's move on to the second application, which is to find the second application of the gradient, which is to use the gradient to find tangent. All right, so geometrically, let me explain what I want here. Let's say I have a shape, right, a surface in 3 dimensions, but it's a 2-dimensional surface given to you by a function of 3 variables is equal to a constant. Okay, so you could think of, for example, a sphere that's x squared plus y squared plus z squared is equal to, let's say, 1, right? That's a radius 1 sphere. So there are, a lot of surfaces given in this form. And the question is, if I have a point on the surface, can I find the plane that is tangent to this? So this is at the point P0. I want to find the tangent plane at P0 to the surface F is equal to a constant C. So what is this? Well, observe the following, that what does it mean to be tangent to this? Well, consider any curve, gamma of t. So it's a parameterized curve. Let's say it's parameterized by x of t, y of t, z of t, right, lying on the surface. All right, so here's your surface constant. You have your surface defined by this function, and let's say it goes through this point P. So let's say gamma at 0 is exactly this point P0. Now, what really is the tangent plane to the surface? Well, in a sense, if I have a curve going through P0 here, it has some sort of velocity, and it makes sense that the velocity vector of my curve gamma t, this point here, I want to be contained on this tangent plane. All right, the tangent plane in a sense is it's something flat, it's something linear, and it best approximates my shape here, my curvy shape, my surface in blue here at P0, and I want at P0 this plane here to just brush up against this point, and that's what the tangent plane should be. And in a sense, that just means that for every single vector that is tangent to this, so every single curve passing through this point P that lies on this blue surface, its velocity vector, right? The velocity vector of a curve you could think of as the first order, the flat approximation to that curve. It's a line. In a sense, it defines a line through that point P. That direction vector for that line has to lie on this tangent plane. All right, so if I have any curve like this lying on the surface, its velocity at p0 satisfies this following. So there's its velocity at p0. Now by the chain rule, I have d dt, let's say f as a function of t. So if I just evaluate f along this curve gamma t, I get a function of t here, right? So I could take its derivative. So this derivative has to be 0 because I'm confined, my curve is confined to the to the surface defined by f is equal to constant. So if I differentiate a constant, this is 0. Now by the chain rule here, this is the same thing as the following. This is partial x of f times x dot of t plus partial y of f times y dot of t plus partial z of f times z dot of t. I could rewrite this as the gradient of f dotted with the velocity vector gamma of t, right? So at t, so at p0 equals 0, which is at t equals 0, gamma of dot, if I have any, so if I have any curve that goes through p0 at time equals 0, and this curve is confined to my blue surface here, then gamma dot must be perpendicular to my gradient vector of f, right? It's perpendicular gradient of f at p0. So let me recap what I mean. Every single vector at p0 that is tangent to the surface at p0 has to be perpendicular to the gradient of f. All right, so if I now consider the tangent plane at p0 to be the collection of all possible vectors that are tangent to my surface at p0, then every single one of these vectors has to be perpendicular to grad f. In other words, I can characterize a tangent plane at p0 to this blue surface as being given by a plane whose equation, you have a plane equation for a plane, and you want its normal vector to be exactly equal to grad f. All right, so what do we have? The tangent plane t at p0 is the plane with normal vector grad f. All right, so let me do it a quick example here. Let f of x, y, z be equal to the function z minus f of x, y. Find the equation of the tangent plane to f of x, y, z is equal to 0. So let's say this is my surface S, and you want to find the equation of the tangent plane to this surface at any point x, y, z on S. So how would you do this? Well, almost by definition, you need to find the plane whose equation has a normal vector grad f. Now, grad big F is equal to the following. At any single point is minus partial x of little f minus partial y of little f, partial z of big F. If it's of the form z is equal to z minus f of xy, then that's precisely partial z of z, so that's just 1. And so the tangent plane equation at any point x naught, y naught, z naught on S is going to be equal to grad f dotted with the displacement vector x minus x naught, y minus y naught, z minus z naught must be equal to 0. We could expand this out, right? And this gets you minus partial x of f and x minus x naught minus partial y of f times y minus y naught plus partial 1 times z minus z naught must be equal to 0, right? Maybe I should specify these are evaluated at x naught, y naught, x naught, y naught. Now you could rearrange this. This gets you z is equal to z naught plus partial x of f minus x naught plus partial y of f of little f at y minus y naught, or times y minus y naught. But now note that if this is on z, this means that f of x naught, y naught, z naught must be equal to 0, which means that z naught must be equal to f, little f of x naught, y naught. So what you get is z is equal to z naught, which is little f of x naught, y naught, plus partial x of f, x naught, y naught, partial partial y of little f times y minus y naught. So this is the same as the linearization of little f of xy at x naught, y naught. All right, so what's the upshot of this? First, we saw this shortly before we went on break, right? This was if you have a function of two variables, I could artificially construct a graph, right? So in this function of two variables, I could associate it to a surface in 3 dimensions just by writing it as a graph. Z is equal to little f. Now, assuming this graph is nice, and assuming this function is nice enough, then this graph has a linearization, right? We have a good approximation of this graph given by its linearization of this form, exactly this form. And we said that this linearization could be the same geometrically. It's the same thing as interpreting this equation as the tangent plane to the graph at that point here. In this situation here, we've now greatly increased the classes or the types of surfaces we could take tangent planes of. We're now no longer restricting ourselves to graphs, right? This surface here could have been a sphere, could have been a paraboloid, could have been an ellipse, could have been anything. And my claim was the tangent plane equation is exactly given to you by the equation of a plane whose normal vector is gradient of big F. Now, for this to actually give you a tangent plane, one thing we need to check is this actually matches with our old definition of a tangent plane in the case that our surface is actually given by a graph, right? So what I've shown here is, in this example, any surface, little f, any surface that's given by a graph of little f has this form, right? Z minus f of little f of xy is equal to 0. That's the other way of writing a graph. So if I recast it in this formulation and now apply my new tangent plane formula, I get the exact same equation as my old way of doing things. So we see 2 things, right? The first thing is the gradient is powerful in the sense that I can now find tangent planes of surfaces I previously couldn't because I couldn't really write, or I didn't really want to write every single thing as a graph. And well, secondly, it definitely does match up with my old notion of tangent plane given by linearizations of graphs. All right. So this is one powerful way of finding tangent planes. And let's do one more concrete example. Let's find the tangent plane at -2, 1, -3 to the surface x squared over 4 plus y squared plus z squared over 9 is equal to 3. So note that in this case, we do not have the surface as a graph. Nonetheless, we could try to apply our rules above using the gradient to find the tangent plane at this point. So the first step is, what is f in this case? What's f of x, y, z? Well, f of x, y, z, I should set to be this. Because then now I have my surface in the form f of x, y, z is equal to a constant. What's the gradient of f in general? Someone want to calculate this for me? Right, so partial x of big F is going to be 1/2 x, 2y, and y, and then partial z is going to get you 2/9 z. Right. Now at the point -2, 1, -3, grad f is going to be equal to -1, sorry, 2, and -2/3. And so the tangent plane is going to be equal to -1 times x plus 2 plus 2 times y minus 1 minus 2/3 times z plus 3 is equal to 0. This is one, I guess, primary geometric reason we care about gradients. So it gets you easy ways of finding tangent planes to surfaces in general. Okay, so let me recap. Uses of gradients. We found several uses in terms of directional derivatives, how f changes in different directions at a point, and how to maximize direction, which direction your directional derivatives are maximized, minimized, and are 0. We look at the geometric meaning of gradients. So in the sense that if you have a function that is given, have a surface that's given to you by some function of 3 variables that's equal to a constant, you can now find tangent planes relatively easily at any point on your surface. And next class, tomorrow, we'll start with part 3, which is using the gradient to find the minimum maximum of functions and ways to optimize. All right, so optimization.